Hi there, this video is going to go over techniques for solving exponential and logarithmic functions and some of the properties that you need in order to solve them. Let's start by just talking about what an exponential function is. It can often get mistaken for a power function. An exponential function is one that has an exponent of a variable x, so the base would be a number. A power function, on the other hand, is exactly the opposite. It has a base that is the x, and the power is a number. So in that case, the base is what's changing, and in an exponential, the exponent is what's changing. There's also a relationship between exponentials and logs, which is why we group them together. They are inverses of each other, so that means that the input from one of the functions becomes the output for the other. Their domains and ranges will switch places when you switch between exponential and log. So for example, if we had an exponential function that looked like this, the equivalent log function would have the same base, but it would take the old output and make it its input, and the old input, and that would become the output, so they would switch places. You could also do this starting as a log. Again, keeping the base the same. What used to be the input is now the output for that exponential function. They've just swapped places. This is also apparent when you get to the graphs of the two of them. An exponential function will always have a y-intercept of 1. In this case, I'm using a positive or a base bigger than 1 as an example, so it's increasing. For a log function with the same exact base, all of those ordered pairs will reflect across y equals x. So it will have an x-intercept at 1 instead of a y-intercept. And the shape will look like it could be reflected across y equals x. This is going to be pretty important when we go to solve, because if you notice, a log function doesn't have any x values that are negative. So it is not going to allow you to plug in negative numbers, which means as we solve for x, we're going to have to check that we're not getting solutions that would create negative inputs. That will be important once we get to the log side. But first, let's start with our exponential functions, starting with example 4 here. So whenever you notice that your x is trapped in the exponent position, you have to get it down to be able to do operations with it. And in order to move it down, we're going to either take the log of both sides and use the log property for exponents, or just change forms to log form. In this case, if I do that, it would be a log base 4, because it should have the same base as the exponential. And what used to be the output for this exponential will be the input for the log. And this is nice because when we bring that power down, we can now just do some basic algebraic operations on the right-hand side to get the x by itself. So my next few steps will be to get the x alone by adding 1 to both sides, and then dividing by 2 on both sides. Now, please note that the test for this unit is not going to allow a calculator, so likely this would be your final answer. You can also use change of base formula to rewrite this piece, so it's possible that you could also see an answer that looks like this, which is just using change of base to make them both log base 10. That is also equivalent. For this homework, I believe the notes or the directions do say to solve using a calculator and round to 4 decimal places. So if you do that, you might need to use this bottom formula if your calculator does not have the change of base option on it. And for this one, I got 1.6887 when I used the calculator, either with this version up here or this version right here. Okay, on example 3, we have something that's very similar. It is currently exponential. The main difference is on this side, we have exponential on both sides of the equation rather than just one. So changing the form from exponential to logarithmic is not actually going to help us, because that right-hand side, which in our current problem has an x in the exponent, would end up inside the log again anyway. So for this one, I'm just going to take the log of both sides. So all that looks like is you're applying that operation of log base 10 to both sides. The reason this actually benefits us is that there's a log property that says you can take the exponents on the input and move them out front. So that's going to help me bring the x's out of that trapped position. Now when you do that, just be careful because that whole expression gets multiplied to the log. So I'm using parentheses to remind myself that it needs to be distributed to both of those terms that came from the exponent. So I'm going to go ahead and do that distribution next. Just distributing log base 2, or log of 2, which is just a number, next, I need to gather the x terms together so that I can get the x out from those two terms. So I'm going to move terms from side to side. It doesn't matter which direction you go, as long as on one side you have terms with x and on one side you have terms without an x. All right. So that helped because now on one side we have two terms that each have an x in it. So we can factor out that x and just write down everything that's left over when you take an x away. That right-hand side hasn't changed. And now if you remember that logs are really just numbers, this is just some messy decimal that I'm keeping in a nice clean format, then you can just divide by this whole expression and that will help you get your x by itself because it's just a number. You're allowed to divide by numbers. So that means we're going to have x equals right-hand side divided by the coefficient from the left-hand side. And again, if you don't have a calculator on the test and this problem pops up, you would stop here. This is as simplified as it can get. But if you're going to use a calculator just to get a final answer, then I got negative 2.1861. If you got something different, I would double check that you're using parentheses. You do need parentheses on the top and on the bottom for the calculator to divide correctly. Okay, next we're moving on to the back side of this worksheet, example 9. This one's also exponential because it has an x in the exponent position, but we have different bases, which means we have to do some kind of alterations. Now, if you notice that 9 and 3 are related to each other, you can write that base of 9 in terms of 3 so that they'll match. Now, I'm going to raise both sides to the power of x just so that it matches what's in the equation right now. And if you are familiar with your exponent properties, this is equal to 3 to the power of 2 times x. And since multiplication is commutative, this is the same thing as x times 2, which means we can go ahead and write this as 3 to the x squared. Now, it's kind of a long-winded way around it, but I wanted to make sure it was clear how I was able to just switch the exponents like that. It really comes down to the fact that it's multiplication in the middle. So I'm going to go ahead and rewrite this 9 to the power of x as 3 to the x squared, since we've proven that that's all equal to each other. And if you check carefully, you have something that is quadratic now. You have a term that's squared, a term that's not squared, and then a constant. If it's unclear that this is quadratic, you can use something called U substitution, where you put a different letter in place of something that's making the equation look more complicated, and then that might help you to solve it a little easier. So if I put u's in place of the 3 to the x, then you might have an easier time seeing that that really is quadratic and we're allowed to factor it. So I'm going to go ahead and factor. And we can solve each factor equal to 0. Now, here's the trick though. Don't forget to put the 3 to the x back into the equation. We're not solving for u, we're solving for x. So my last step is to put that back in. And here's a good place to check our domain and range restrictions. On the left-hand side, I can clearly see that x should be 1, because that's the only way to make the base come out the same on either side. But on the right-hand side, there is no power that I could possibly put on this 3 that would give me a -2, because back on the other side, when we looked at the graphs, the exponential function never goes below the x-axis. It can't have a y value that is negative without having some kind of transformation applied to it. So on this side, this one does not equal -2, and it just won't give us a solution. So it means we only have one solution in this case, and it's 1. Okay, on number 12, I'm just going to help you set this one up because it is actually similar to the one we just talked about, but it doesn't look the same right away. In this case, we have this -x and +x and then a constant, so it's kind of like the quadratic in some ways, but doesn't really look quadratic because there's nothing squared. To modify this, I'm going to multiply both sides by e to the x. Remember, you are allowed to multiply an equation by anything as long as you do it to both sides. So if you ever see something that just might look easier if you did some multiplication, usually like fractions maybe, feel free to do it. You're allowed to do it as long as you do it to both sides. Now I'm going to have to be very comfortable with my exponent properties. When I multiply two things that have the same base, their exponents will add. So I have 6 times e to the power of now 0, because -x plus x would be 0. So that's just a 6. And then I'm going to keep going, distribute this over, and distribute this over. Again, the powers will add. And then 0 times e to the x is still 0, so it looks like I really didn't do it to both sides, but I did. We just talked about this guy. That can be rewritten as e to the x squared. And now it looks more quadratic, and you can proceed exactly the same way we did on example 9. All right, our very last example for today is one finally with logs in it. Logs, you're going to use a lot of those log properties for expanding and condensing. Here I have a plus in the middle, which means that I can multiply the inputs on my logs and combine them together because their bases match. And the reason I want to do that is because right now in its current state, I can't change to exponential form. And exponential form is the only way to get those x's out of the log. So I need to combine them first into a single log, then change forms, and then proceed. So I'm first going to do that multiplication. Log base 2. The input is the product of these two. So just carefully FOIL, because I know this one over here looks a little funky. That's -x squared plus x minus 2x plus 2. And now that we're in a single log, we can change it to exponential form. The base will stay the same, the log's output will become the exponent, and the log's input is the output for the exponential. So 2 to the 1 equals all of that input, and now it's just changed to an algebraic expression that you'll solve using any quadratic method you like, factoring, completing the square, quadratic formula, whatever you want. I'm also going to combine terms, and it looks like this would be nice and easy to do as a factoring problem. So I'm just going to take out a -1, divide both sides by -1 to get rid of those negative signs, and then we can factor out an x and set each one equal to 0. Super simple. Now if you notice down here at the bottom, I've got this test section. So earlier I mentioned log equations do not have an ability to have a domain that is negative. So we have to check our solutions when the original equation was a log to make sure none of these solutions are creating negative inputs for those logs. And it might not be that obvious at first, especially when there are operations happening to these logs. So for example, here it's not just the x value, it's the x value plus 2. So at first you might think, oh, -1, you can't do that. That's negative, right? Well, when we go to plug that into the log function, there's that -1, that turns into a +1, which is okay. It's fine. So far, no problem with that -1. If I plug it into the other log, we get this double negative, which turns into a 2, so that one's also fine. So it seems like that x value of -1 doesn't actually cause an issue because of the transformations on the log function originally. Let's just check the 0 also, because sometimes positive ones or 0 can become negative depending on the transformations happening to that log. In this case, again, it creates two positive numbers, so we're okay with it. So in this case, it checked out. Just be wary, there is at least one problem on this worksheet where some solutions are extraneous. That means you found them through algebra, but they weren't actually solutions of the problem. So just keep your eye out for those. All right, so homework for tonight is finishing everything else on this worksheet. You are welcome and encouraged to work together. Send me an email if you get really stuck, and I can try to help you send you things back. And there is an online submission for a few of these questions just so you can check how you're doing. All right, have a good day.